All right. So the first question that we ask are how to find like the derivative of like an inverse trig function, and we know how to do that by using the derivative of the inverse. So if I want to find the derivative of f inverse with respect to x, so this is the derivative of f inverse. See that? This is equal to 1 over f prime of f inverse of x. So say I want to find, the derivative of, say, y is equal to, I don't know, let's say the sine inverse of x. So I'd consider this the inverse function. So I consider this f inverse of x is equal to the sine inverse of x. So that would make f of x just the sine of x. So this is the inverse, this is the inverse of the inverse, or, the not inverse. So in order to find the derivative of this thing, I'm going to need to know the derivative of f. So I'm going to need to know f prime of x, which we know is the cosine of x. And I'm also going to need to know f inverse of x, which is this thing. So when we set this up, this piece becomes, this is equal to 1 over, well, f prime is going to be the cosine of, well, it's the cosine of f inverse, where f inverse is the sine inverse. So this is the cosine of the sine inverse of x. So it's the composite of those two functions. So the way we know how to simplify this composite function is, just like, your trigonometry class that you took, or even a pre-calc class, we do it there too. What I want to do is I'd like to write this a couple ways to look at it. I like to write this as the cosine of the cosine inverse of a thing, and then the cosine and cosine inverse would cancel. Or I can just write this sine inverse function as, as a cosine function, and we can figure out what the denominator is. So there's a couple ways to go about it in the arrow part. So what I want to do is I want to find the cosine of the sine inverse of x. So what I'm going to do is I'm going to let I already call it something y, but I guess I'll just call it again. Let's say let y is equal to the sine inverse of x. I think I'm near the edge of my screen. You can kind of see that. So what I'm going to do is, I have y is so this now is this is the cosine of y now, because I called it I called the sine inverse equal to y. So once I know the cosine of y, I know that this expression is the same as this, which would be the same as this denominator. So what I'm going to do is I'm going to figure this thing out. Well, I can't turn a sine inverse directly into a cosine inverse, but I can take a sine and turn it into a cosine using the Pythagorean theorem. So what I know is I could sine both sides. So this would mean the sine of y would be equal to x. Sine this side, sine this side, this side, and sine inverse will cancel. So what I'm going to do is I'm going to take the sine of y and turn it into a cosine of y. We can do that with the Pythagorean theorem. So, the Pythagorean theorem says that the sine squared of y plus the cosine squared of y is equal to 1. And I know the sine is x. So I'm going to plug that right into here. So x squared plus cosine squared of y is equal to 1. So solving for cosine, you'd subtract x squared, so 1 minus x squared. And then you'd square root. So the cosine of y is going to be the square root of 1 minus x squared. And remember, the cosine of y is the same thing as the cosine of the sine inverse. So what we figured out is that's the denominator. This is 1 over, well, this thing. So this is equal to this. So this is the square root of 1 minus x squared. Which is why that's true when you look it up in the table. So we're just using the inverse function along with the Pythagorean theorem. A little bit of trigonometry. We'll do the same thing again with the tangent function. Because I'm either going to give you find the inverse of the sine, or find the derivative of the sine or the tangent function. It's my two favorites. So it'll be one or the other. So again, instead of y being equal to the sine inverse of x, let's do y is equal to tangent inverse of x. And then we have, we have to move through the Pythagorean theorem again. So say y is equal to the tangent inverse of x. I'm trying to find the derivative of this function. Well, this function is my inverse function, so I'm trying to find the derivative of this, inverse of x. So in order to find the derivative of the inverse function, the derivative of the inverse function, I need to know the derivative of f of x. Well, if f inverse is the tangent inverse, then f of x is just the tangent function. So in order to find the derivative of the inverse, I need to know the derivative of f, so the derivative of this thing, and I need to know f inverse, which is this thing. So f prime, the derivative of the tangent is the secant squared of x. So this is the secant squared of f inverse, or the secant squared of the tangent inverse. So this becomes 1 over the secant squared of the tangent inverse of x, which is the same thing as it's this function squared, so we can write it like this: the secant of the tangent inverse of x squared. That's what it means to be squared. I'm squaring the entire expression, so I'm squaring the entire thing. So what I need to do is I need to know what the secant of the tangent inverse is. So do it over here. So let's find the secant of the tangent inverse function. So we'll do the exact same thing. What I'm going to do is I'm going to call this the secant of y. So that means the tangent inverse is equal to y. So the tangent inverse, so y is equal to the tangent inverse, to the same order we had last time. So y is equal to the tangent inverse of x. And I can't turn one trig function into other trig functions in its inverse form, so I have to turn it into its regular trig function form. So, I'm going to write this as the tangent of y. So we know that the sine squared of x plus cosine squared of x is equal to 1. I apologize. These are all functions of y's. Tangent of y. So these are all y's. This is equal to 1. So if I want to come up with a tangent, I have to divide everything by cosine squared. So sine squared over cosine squared is tangent squared of y. Cosine squared over cosine is 1. And 1 over cosine squared is secant squared. And what I know is I know the tangent of y is equal to x. So stuffing x into the spot, we have x squared plus 1 is equal to the secant squared of y. So solving for the secant, which is I'm trying to find, it's going to be the square root of that expression. So this is going to go into here. So this is equal to 1 over this thing squared, so square root x squared plus 1, and the square will get rid of the radical, so this is 1 over x squared plus 1. And the formula gives you is 1 over 1 plus x squared, but those are equivalent. It's the same exact thing. So that's really where those things come from. It's just manipulation of the Pythagorean theorem along with this derivative of the inverse. Kill my battery to plug this thing in. Okay. I wish I had my laptop. Oh, well, this will do. The next thing that we covered in our quiz was derivatives. Logarithm. They call it logarithmic differentiation. But all it is using the rules of expansion of logarithms to be able to take derivatives. So if you remember, like again from an algebra class, your 3 rules were this: if I have the log base, just say log base b of a plus the log base b of capital B, I guess, is going to be equal to the log base b of a times b. So we used to go this direction in algebra. We go this direction in calculus because in this direction we have a product rule. In this direction we have a sum rule, and sum rules are quicker. So, if I turn this into a subtraction here, this is going to be addition, division. I'm just going to write them as natural logs because it's faster, but it works with all logarithms. So the natural log of a minus the natural log of b is going to be the natural log of a divided by b. It works with all bases. Natural log is just base e. And then, let's see. C times the natural log of a is equal to the natural log of a raised to the c power. So usually we're going in this direction when we're taking derivatives. We want to expand the logs as opposed to, condensing the logs. One of them uses this rule almost exclusively, and the other one will ask you to expand first. So if I ask us to find the derivative, for example, it says logarithmic differentiation. What they're asking you to do is expand first and differentiate second. So say a y is equal to x squared times the square root of x plus 4. Something like that. We can use derivatives. We have the techniques to do this. I know that this is a power rule. So, you can do derivative of the first times the second plus the first times the derivative of the second. And knowing that this thing is a chain rule, so derivative of the outside times derivative of the inside. But we can use expansion. I can use this rule to write this. So I can say the natural log of y is going to be equal to the natural log of this thing. What I do know is multiplication turns into addition. So this is going to be the natural log of the first plus the natural log of the second. I'm going to write this radical as a power. Square root is the same thing as 1/2 power. We practice that enough in differentiation. And then the last thing, I can use these powers to expand them. So this 2 can go out front. This is 2 natural log of x plus 1/2 natural log of x plus 4. That's the natural log of y. Taking the derivative of this is messy because, product rules and chain rules and so on. Taking the derivative of this I know there's a little bit of a chain rule for this one, but it's really quite simple. So if I took the derivative, that's what we're going to do, take the derivative. We'll do the right-hand side first because it's the easiest, and we'll talk about this one next. So the derivative would be, the derivative of the natural log of x is going to be 1 over x. So this would be 2 times 1 over x. Because this is a constant, so you can just ignore the constant, take the derivative, and put the constant back in. And this would be the same thing, 1/2. The derivative of the natural log of something is going to be 1 over that something. Of course, times the derivative of what's inside, but the derivative of x plus 4 is 1, so it's a little bit nothing. So that's the derivative of the right-hand side. But this expression here is an implicit function because it's not solved directly for y. This is explicit. This is implicit. So when I take the derivative of this thing, I have to take the derivative implicitly. So the derivative of the natural log of something is going to be 1 over that something. But every time you take the derivative of an expression with y, it's got to be followed by dy dx. So derivative of this is going to be 1 over y, dy dx times. So in order to solve for dy dx, which is, I'm trying to find the derivative, you go basically to find the derivative of y. So what I can do is I can multiply both sides by y because I have y in the bottom over here. So this says dy dx is going to be equal to y times, this expression. So 2 over x plus 1 over 2 times x plus 4. And y is this original expression. So dy dx, the answer to this thing is going to be x squared times the square root of x plus 4 multiplied by 2 over x plus. So we're really just using these rules to make it simpler. Now, it kind of seems like a parlor trick. Like, hey, that's cool. I could have already taken the derivative here. So logarithmic differentiation didn't give us anything important besides another way to do it. But there are functions out there where you have to use logarithmic differentiation because there are they don't live in a particular class of function. So like a really good example of that would be something like b, which would be y is equal to, I don't know, let's say x to the, I don't know, x squared plus 3. Heck, let's not even make it that messy. Let's just say x to the x. It doesn't need to be that hard. So just x to the x to the x power. This expression is neither polynomial nor exponential because, you know, a polynomial function would be like x cubed, right? You know, it's just a power function. Its derivative would be easy. It's 3x squared. Y would be, say something like 4 to the x. That's an exponential function because the base is a constant and the variable is a power. So, you know, I can find the derivatives of these things. You know, this is 3x squared. This one is 4x times the natural log of 4. So those derivatives are easy, but this function here is kind of a mix of both functions. It's both kind of polynomial because it has a base of x, and it's exponential because it has an exponent of x. So since it doesn't live in any one of these families, I have to use logarithmic differentiation to basically get it out of this form. So these previous rules not being useful to us anymore, those don't help. So what I can do is I can take the natural log of both sides. And what that allows us to do, if you remember rule 3, it allows us to take exponents and turn them into coefficients. So I can rewrite this as x natural log of x. Now this is expanded. It's as far as we can take it. So now I can take the derivative. Now take derivative. Taking the derivative of this thing is the same we just did before. It's 1 over y dy dx because it's explicit. But taking the derivative over here, it has to be well, it's got to be a power rule, I mean a product rule, because that's multiplication between x and the natural log of x. So you have to do the derivative of the first times the second plus the first times the derivative of the second. You know, f prime g plus f g prime, or u prime v plus u v prime, whatever letters you prefer. So derivative of the first is going to be the number 1 times the second, which is going to be the natural log of x. So times the natural log of x. Plus the first, which is going to be x, times the derivative of the second, which is going to be 1 over x. So cleaning that up, this is the natural log of x, and this becomes plus 1. Now remember, I still have 1 over y dy dx. So I have to multiply by y to isolate my derivative. So dy dx is going to be equal to y times this expression. And then this is where you climb back to the original expression, because y is equal to x to the x. So dy dx is x to the x times the natural log of x. Now we're done. So this expression, like stuff of that form, you know, stuff in the form x to the x, forces you to use logarithmic differentiation. There's no, you know, that's the method you have to use. You have to turn it into these things, because I do know the derivatives of these things. I do not know the derivative of that. What else we got? Oh, related rates. We have to do. We can do some of those. Where'd you go? Related rates. Yes. There you are. A simple example. Um, balloon on a bicycle. You know what? Let's do that. So we'll make some stuff up too. So let's do like a balloon and a bicycle. Let's see. What's the bicycle is? So I'll do kind of a picture. If I have like a balloon over here, and I know this balloon is going to be rising. I have a bicycle over here, which I know is going to be moving, well, because I don't really know, but it's going to be moving in basically this direction. I can answer a couple things about this particular triangle that this thing builds. So let's say that let's say the balloon rises at I say 5 feet per second, and the bicycle is riding away at 6 feet per second. I don't know if it can be that fast. Let's say 3 feet per second. Make it realistic. We can ask a couple things about this, about this expression, as far as this triangle is concerned. Let's answer a couple. So when we set this expression up, what I know is I'm going to call this thing x and I'm going to call this thing y, and let's call this distance just d. Depending on your formula, what I'm asking, the formula that this thing starts out with could be different. So if I ask, A, find the rate of change of the area. Find rate of change of the area. So the first thing we have to do is we have to set up an equation for the area of this triangle. And what I know is areas of triangles is going to be 1/2 x times y. So you find the relating equation first before you take any derivatives. So, area of a triangle, 1/2 base times height. Now we take the derivative. Knowing that all these things are changing, so these are not constants. Everything is moving. So moving with respect to t. So the derivative of a would be 1, but it's got to be followed by its derivative. So it would be dA dt. So dA dt. Constants you can pull out, and this is a multiplication. So when you take the derivative of it, it's got to be the derivative first. So dx dt times the second plus the first times the derivative of the second. Knowing that all these things are functions, so really this is an implicit formula where everything is a dependent variable. So from this equation, I actually have to give us some more information because we don't have enough. So when the bike is, let's say, 30 feet and the balloon is 50 feet, say from the start. I'm just going to say from the origin. I'm just going to define the origin because So from this information, from here and also from here, it gives me values for things. So balloon rises at 5 foot actually says that the rising means that this is a rate of change. So this is not y, this is actually the change in y. So from that, I know that dy dt is equal to a positive 5 because the thing is going up, because this y is getting bigger. If this balloon was going down at 5 feet per second, this would actually be a negative 5. I know that the bicycle is riding away, so since x is getting bigger, I should have made it going this way so we could have seen a negative, but it doesn't matter. So since it's going away at 3 feet per second, I know that that dx dt is going to be positive 3. And again, if the bike was running this way, it would be a negative 3 because x is getting smaller. The bike is 30 feet away, so that means x is going to be 30. And the balloon is 50 feet away from the origin, so y is going to be equal to 50. So from this information, I actually have all 4 of these pieces here. So I can find dA dt straight away. So this is going to be, 1/2 dx dt is going to be 3 times y, which is going to be 50, plus x, which is going to be 30, times dy dt, which is going to be 5. So 150. 150. Yeah. All right. So 300, half of 300, half of 300 is going to be 150. So this is going to be equal to 150, and this is going to be feet per second. Actually, it's feet squared per second. It's because it's an area. Not really super concerned about units in a calculus class, and more care about it in a physics class. But the reason why I know that this is going to be an area is because area is 2-dimensional. So that's why this should be. Let's do one more. What if I want to know like this angle here, this angle theta? If I want to know the change in theta. I need a lot of meters. So let's do B. What about the change in theta? So if I'm going to do the change in theta, what I need is an equation that relates theta to, well, these sides, I guess, because these are the given sides. So I know that this side is opposite to theta, and this side is adjacent to theta, and there's a trig function of that. So the tangent of theta is equal to opposite over adjacent. So that's the relating formula because we use trig functions when we work with angles. Now it means I'm going to have to take the derivative of this in order to plug these things in. See if I need to know stuff. We should be fine. Okay, so the derivative of the tangent is going to be the secant squared of theta. But remember, every time you take the derivative of any one of these things, every single thing is a dependent variable, so it's got to be followed by its derivative, so d theta dt. Now this is a quotient, so the derivative of the top, which would be 1 times dy dt, times the bottom, minus the top, times the derivative of the bottom, all over the bottom square. What's nice is I know all those values, so that's done. The other thing I don't know directly is going to be the secant squared of theta. Remember that the tangent is opposite over adjacent, and the cosine of theta is, you know what? Why not just use the trig function again? I know the tangent of theta. Let's do it that way. Let's do the same trig function we just did before, so that it gets more use out of it. There's a couple ways to do this. You know this side, you know this side, you can find this side. So x squared plus y squared is equal to d squared. And then you know that the cosine is adjacent over hypotenuse, so then the secant is going to be hypotenuse over adjacent, so you can do it that way. Or I know that we knew the formula I just showed you in the very first one, tangent squared plus 1 is equal to the secant squared theta. And the tangent is going to be y over x, where y is going to be 50, x is going to be 30. So this is going to be 50 over 30 squared, plus 1 is going to be equal to the secant squared of x, so secant squared of theta. So 5 over 3. So this is going to be 25 over 9 plus 1, which is going to be 9 over 9. So this is going to be 34 over 9 is going to be equal to the secant squared. So I can plug that in. So now we have 34 over 9 times d theta dt is equal to, again, remember that if you did x squared plus y squared is equal to d squared, I can kind of prove this to you real fast. So x squared is another way to do it is x squared is 50 squared plus, what is that, right? Let's check 30 squared. 30 squared plus 50 squared would be equal to d squared. So 900 plus 2500, yeah, is equal to d squared. So this is going to be 3400 would be equal to d squared. So square root of 3400 can't be that easy. Okay. Screw that up. Times 10 or squared. I will get a calculator in a second. You'll figure out that you'll get the exact same number. You're going to get this over this, which is 34 over 9. Well, technically, it would be like oh, that's why, because it's secant squared. Well, who cares? This is going to be the square root of 3400. I'm not even going to simplify it. It's going to be equal to d. So this is equal to the square root of 3400. And this thing right here is 30. So the secant, the cosine is adjacent over hypotenuse. So the secant, which is reciprocal, would be hypotenuse over this. So the secant squared is going to be this over this squared. So what it would be is secant squared would be square root of 3400 all over 30 squared would be equal to the secant squared. And 30 squared is going to be 90. And you'll see that this will simplify this. 900. So this is going to be okay. Dy dx is going to be 5 times x, which is going to be 30, minus y, which is going to be 50. Dx dt is going to be 3 all over x squared, which is going to be squared. So it's a 0. Why? Why is that 0? Okay, that it is. Just wondering why. That's interesting. it's just lucky. It's kind of crazy. It must be growing at a relatively good pace. It must keep its same shape then. So whatever. So 150 minus 150. This is going to be 0 over 9, which is going to be 0. That's not usually 0 is the problem here. So so this is going to be 34 over 9 times d theta dt. So if that number wasn't 0, I'd have to send this to the other side. So d theta dt is going to be equal to 0 times 9 over 34, which is still going to be 0. So that's strange. I guess I got to be careful when I'm making things up, but I see why. Look at that. I just, these numbers and these numbers, they end up, when this thing grows, I guess it keeps its shape. You know, it really means it's going to be a similar triangle at all times, and that's just yeah, that's cool. It's neat. Okay, so this will be radians per second. Radians per second. And it's really kind of the gist of those. It's another one. You know what we should do? We should do one more. Let's talk about how D is changing. And that'll be our last one. And then we'll move on to maxes and mins. And I will grab a calculator because we're going to need it. So C, a find rate of change of D. So what we need is, I guess we know that's 3,400 square root of it. We might need it sometime. The relating formula between x, y, and d is, since this is a right triangle, is going to be the Pythagorean theorem. So x squared plus y squared is equal to d squared. So make sure that you write your relating formula first and then take the derivative second, okay? Because all these things are possibly changing. Sometimes they're not. You know, for instance, if this was like a ladder or something like that, if this was connected, then, you know, this might not be changing. So the derivative of this is going to be, you know, 2x dx dt plus 2y dy dt is going to be equal to 2d dt, and the 2's will cancel. And what's nice is I really want to find this dt, so, you know, these 2's will cancel. So dividing everything by d, this is going to x dx dt plus y dy dt all over d is going to be equal to d. I have all these values. I know x, which is going to be, what is x? X is 30. dx dt is going to be 3 plus y, which is going to be 50. dy dt is going to be 5 all over d, which is the square root of 3,400, calculated that previously, would be equal to d dt. And you could, it's going to be messy because that radical, but, you know, you could just plug it in the calculator and figure out what it is. All right, so we'll do max and mins on a closed interval first, and then we'll do it on an open interval second. Right back to the calculator. All right. So, all right. Next, we'll do so max and mins and closed intervals. Let's do actually I could just pick a couple out of the book. Gotta be some more interesting than this. Okay, so let's do this. Big one up this. I don't know why. But that's okay, that'll be fine. So for instance, I want to find example. So we're gonna find absolute max and min on closed intervals. Now, all I know is every continuous function will obtain its absolute max and absolute min on a closed interval. So if you look at any curve, I can do something like this. As long as it's continuous on a closed interval, it's got to obtain its max and min. So even if it looks like that, or it looks like this, or it looks like this, we can see that for this particular one, this is going to be its maximum right here, and this is going to be its minimum. In this case, this looks like a monotonic function. This is going to be its max, and this is going to be its minimum. And over here, it looks like this is its max, and this is its minimum. So we can see is sometimes the maxes and minimums can happen inside the interval, and sometimes they can happen at the endpoints. So that's what we have to do is we have to first check to figure out where the derivative is equal to 0, so we can find these particular spots here to where I have possible maxes and mins. Once we check those x values, then we also check the endpoints to see what one's bigger and what one's smaller. So there's 3 different versions of different graphs. So I'll start with the polynomial because it's easy. So say y is equal to, say, x squared minus 6x plus 16. So if I want to determine its absolute max and absolute min, we're going to say on what, 3? So x at 3. So let's go from say 1 to 4. So the first thing I have to do is find its critical points. Where the critical points are when f prime of x is equal to 0. So first I'm going to take its derivative. So this is going to be 2x minus 6, and then I'm going to set it equal to 0. Solving for x, you get 2x is equal to 6, so x is equal to 3. So this is one candidate for a max or a minimum, and those are the other candidates. So you always check its critical points and then also its endpoints. The biggest one being the max and the smallest one being the min. So we plug these back into the original function to figure out what one is the largest, because remember, these are the y-values. So now back into f of x to determine the biggest and smallest. So first we'll do f of we can do the critical point first and then the endpoint second. So we have to do them all. 3, 1, 4. So 3 gives me 7 back. Let's make sure. So this would be 3 squared minus 6 times 3 plus 16. 9 minus 18 is negative 9, plus this is a 7. So this is gives me 7. This is going to be 11, and this one right here is going to be 8. So I can see my maximum is going to be the the largest y value, which is going to be this one. This is my absolute max. So this is going to be my absolute max. And my absolute min is going to be the smallest one, which is this one. So one way you can say is the absolute max is 11 at x is equal to 1, and the absolute min is 7 at x is equal to 3. Well, you can really just say that. This is pretty clear. This is the max and this is the min. So if you just label this the absolute min and this the absolute max, I'd be good with that. But the reason why it's the max and min is this is the min because it's the smallest y value, and this is the max because it's the largest y value. What's nice about your closed intervals is the absolute max and absolute min will only happen at these candidates. So you don't have to do anything special. We just find its derivative, set it equal to 0, check its endpoints, and then figure out what's bigger. If I have something like y is equal to I don't know, say 5 to the x, the exponential function. Again, critical points happen when the derivative is equal to 0, so you know your critical points. This is when f prime of x is equal to 0. So the derivative is going to be 5 to the x times the natural log of 5 is equal to 0, divided by the natural log of 5. So 5 to the x is equal to 0. And if you try to solve for this, you'll see that you don't get an answer back. What you could do is you could log base 5 both sides, log base 5 this 5 to the x, log base this 5 of 0. So this will get x is equal to the log base 5 of 0. And if you try to find the log base 5 of 0, which is the same thing as the natural log of 0 or the natural log of 5, this will give you an error, it'll give you undefined. So this has no critical points. This particular exponential doesn't have critical points. If you graph this, 5 to the x looks like this. It's an exponential function. Oh, I need to give. And let's say, let's go -1 to 4. No, let's go -1 to 2. So if I went from -1, let's say this is -1 all the way to 2. So it looks like that. The reason why this doesn't have critical points is because remember, a critical point is where it has like a hump like this. That's a critical point. It's got a horizontal tangent line or something that looks like this is also a critical point. It's got a horizontal tangent line. These are when the derivatives are equal to 0. The derivative is never equal to 0. You can see that this is an increasing function. The derivative will only be positive. That's why this is never 0. This is always a positive number. So it's absolute max and absolute min are only going to happen at the endpoints. So since it's got no critical points, I just plug these things into the function and figure out what one's smaller and what one's bigger. So now we check, what is f of -1? Well, this is 5 to the -1, which is a fifth. And then we have f of 2, so this is 5 squared, which is equal to 25. So you can see that, a fifth is going to be your smallest one, and 25 is going to be your largest one. So this is your absolute min here. And this one will be your absolute max. Yeah, let's do a trig function too. Might as well see one. say y is equal to, let's say the sine of x. Let's go pi over 3. Let's go 30 degrees. Pi over 6 to the pi. Yeah, I like it. Pi over 6 to pi. Okay. Yeah. So what we're going to do is get critical points. This is when f prime of x is equal to 0. So this is when the derivative of sine is going to be cosine of x is equal to 0. And remember, the cosine of x is equal to 0. It's the x coordinate. So when you're looking at like the unit circle, you look at the unit circle for the cosine will equal 0 here and here. And since I'm only from, pi over 6 to pi, the only spot it's going to be equal to 0 is going to be pi over 2. So this is when x is. That's one critical point. That's the only critical point on that interval, because since I stop at pi, which is halfway around the circle, I never get to that. Now we also have to check the endpoints as well. So we'll check this and those three as well. So remember back into the original function, I need to know what is the sine of pi over 2, so pi over 6. Let's do the critical value first, pi over 2, and then we'll do the endpoints as well, pi over 6, and then the sine of pi. Well, if we're looking at the unit circle, pi over 2 is right here, and the sine value is going to be the y coordinate, so this will be 1. Pi over 6 is 30 degrees, which is going to be here. That should be a half. Let me double check. Yep, half. So half. And then the sine of pi will be right here. The sine is the y coordinate, so this is -1, 0, 0, 1. All I know is this is a half. But the sine being the y coordinates. So your maximum is going to be your largest number. So this is your largest output, 1. So this is your absolute max, and this will be your absolute min, because that's the smallest y coordinate. Next we'll get to is what if it's not on a closed interval? How do we handle these things? Well, we might not always ask for the absolute maxes and absolute mins. I just want to know its local maxes and local mins. So for instance, if we have like a parabola that opens like this, parabolas go down forever. It will have an absolute max, but we consider this like an absolute or a local max, even though this is your biggest number. This is going to be your maximum. And this has no local min. No absolute or local min, because these go down forever. So there's not a y coordinate I can isolate this thing. Now you can have functions that do something like this. They can bounce back. So this will be a local maximum, and this will be a local minimum. Around this area, that number's the biggest, and around this area, that number's the smallest. So that's what we mean by local. In those general areas. So local max, local min. This has no absolute max or absolute min because it goes down forever and up forever. So in these questions, I don't really ask for absolute max or mins. I just want to know if it's going to be a maximum or a minimum. So how I know that this is going to be a maximum is the function increases before it and decreases after it. So if it increases before and decreases after, it's got to be a maximum. And this here, it's going to decrease before and increase after, so therefore that was got to be a minimum. So we're going to use that idea of intervals increasing and decreasing to identify if these things are maximums or minimums, local maximums or minimums. I know I'm moving quick, but this is all recorded, so you can always kind of go back and check it out. I got to put the kids to bed sometime. Let's see how this is working. So not absolute max and absolute min. We're going to find local max and local mins at open intervals. So find any local extrema, which is really the same thing as local max or local min. So this is one word to say min or maxes. That's what I mean by extrema. I played hockey tonight for the first time in a couple months, and I am now feeling it. So let's start straightforward with something that's. Let's start with a polynomial, so that's a little bit easier. So let's just do this number here. So A. This marker's dying a bit better, I'm sure. F of x is going to be x to the fourth minus 8x squared. 8x squared plus 16. Okay. So we no longer just test the critical points and the endpoints because this is an open interval. We're just looking for extrema. So I'm only looking for intervals where it's increasing or decreasing. And the only spot, so say I have a function that looks, I can get as messy as I want. What's nice about your intervals is these spots are critical points because they have horizontal tangent lines. This is when, this is when the derivative is equal to 0. F prime of x is equal to 0. So what's nice about this is these are the only spots where your intervals will change from increasing or decreasing. So whatever the x-axis is, say this is your first critical point, this is your second critical point, this is your third critical point, and then let's say it just continues forever in this direction. Notice that from minus infinity to this first critical point, this function is always increasing. It's always going uphill. And then from this critical point to that critical point, so from C1 to C2, this function is always decreasing. I know the rate of change in which it's decreasing also changes, but it's going downhill, so it is a decreasing function. And then between these two numbers, it's increasing, and then from here all the way to infinity, it's going to be decreasing. So the only spots that these things change basically, from increasing, decreasing, increasing, decreasing, the only spots that they change are at the critical points. Now, a graph is not proof, so when I prove this increasing and decreasing, I have to plug a value in here and then show that its derivative is positive here. Because if it's positive here, it's positive everywhere, because it's going to share the same increasing on this entire interval. So same thing here. I'm going to pick some number in here, say that one. I'm going to plug it into the derivative. The derivative is going to spit out a negative number, which means that interval is going to be decreasing. I'm going to plug a number, I don't know, somewhere in this interval here, and on that graph, and the derivative is going to be positive. So it's increasing on that interval, it's decreasing on this interval. So once we see this, increasing and decreasing means it's got to be a max. Decreasing and increasing, it's got to be a min, and so on. So it's kind of what we're going to do with this function. We're not going to draw any pictures. I'm just going to isolate these intervals and do it, because a graph, a graph of your calculator is not proof. The reason why is because your calculator is not fine enough to be able to do every single point. All it is graphing so many points. And it is really possible in between any of those 2 points that graph could do really funny things. So it's, that's why a graph technically is not proof. It's not nearly accurate enough to do it. So first we find the critical points. So this is when 4x cubed minus 16x is equal to 0. I can factor this now, so I can see that I can factor out a 4x, and this would be x squared minus 4 is equal to 0. And that's a difference of squares, so 4x times x plus 2 times x minus 2 is equal to 0. So, I have 3 factors here. 4x being equal to 0 means x is equal to 0, and x plus 2 is equal to 0 means x is equal to negative 2. Then x minus 2 equal to 0 means x is equal to positive 2. So if we're looking at the intervals that this happens, I have 0, I have -2, and I also have +2. Those are my, those are where these things are making cuts. So what I'm going to do is I'm going to test these intervals. So my intervals are going to be, well, this first order number is here. This is going to be, minus infinity to -2. This interval is going to be -2 to 0. This one's going to be 0 to 2. And then remember, this one goes off to infinity. So this is going to be 2. I want to see if they're increasing or decreasing and so on. So we can see if it's due to this stuff. We can check mins and maxes. So what I'm going to do is I'm going to pick an x value out of these intervals. So I'm going to try to pick nice numbers, but it doesn't have to be perfect. So any number that lives in here, I'm going to say like maybe -3. So -3 lives in that interval. Here I'm going to pick -1 because 1's usually a nice number to pick. Here I'll pick +1, and here I'll pick 3. I just need that x value to live in those particular intervals. And then what I'm going to do is I'm going to plug these things into the derivative. Plugging them into this thing, to the derivative. If you plug it in and its output is positive, it's going uphill there. That means it's increasing. So I'm just going to plug these things into that function and see what happens. So for 4x cubed minus 16x second 2. Okay, so let's just do memory. X cubed minus 16x. Ask. Okay, so I have -3, -1, 1, 3. So this number gives me -60. So since this is a negative number, this is decreasing. This interval is decreasing. When I plug -1 into this function, I get +12. A +12, therefore this is increasing. Plugging 1, I get -12. Therefore this is decreasing. And when I plug in 3, I get +60. Therefore this is increasing. So you have to show the values of the derivatives to prove it's increasing. You have to show that. That's the calculus that we're doing. All right, so what's nice? Come on, this is decreasing first, increasing after. That means this x is equal to -2. That means x equals -2 is a local minimum. Here at 0, it increases first and decreases second. So that means x equals 0 is going to be a local maximum. Increases first, decreases after, a local max. And then over here, it's going to be at 2, it decreases before 2, and then it increases after 2. So that means x is equal to 2 is going to be a local min. And that's what I'm asking for when you find your local extrema. And I don't really care what one's absolute. This here, yeah. I think these will share their absolute min. There won't be an absolute max because it go on forever. But I don't really care. Just find the local extreme is really what I'm worried about. Let's do your quiz question, because I think people struggle with that one. But I'd like to explain it, a little more than what you just saw in the quiz. Well, I really hope you can see this pretty well, because it's been spent an hour and a half on this so far. Wow, this is messy. Ah. Yeah. All right, so let's say number B, f of x is equal to x squared square root of 5 minus x. So this was your quiz question. It'll just kind of explain. There's one point that a lot of people missed, and it's because the domain of this thing, since it's a radical, means it's going to have endpoints. It's going to, the endpoints are going to happen with, what's underneath here is equal to 0. We'll see in a minute here. So pretend we don't see that. So the first thing we have to do is our critical point. So I have to find its derivatives. So f prime of x is going to be, this is a product, so I have to do the product rule. And remember, this is the same thing as, so the derivative first is 2x times the second, which is going to be 5 minus x, plus the first, which is going to be x squared, times the derivative of the second. Well, this 1/2 is going to go out front, times 5 minus x to the negative 1/2, and then times the derivative of what's inside, which is going to be a negative 1. And we'll clean this up a little bit. So this is, 2x root 5 minus x, negative, positive, positive. This is going to be minus. This is going to be x squared, and on the bottom, I'm going to have a 2, and this radical's on the bottom because of negative 1/2. So 2 square root of 5 minus x. I know I can figure out where it's equal to 0, but remember, it's also where it's undefined as well. So it'll be a little nicer if we combine these two fractions. And the way you combine them is you're going to want to get common denominators. So what I want a bottom to be, 2 root 5 minus x. So I'm going to have to multiply the top by 2 root 5 minus x. So, now we're going to have that common denominator of 2 root 5 minus x. Now I'm going to have this numerator minus this numerator. So, well, this is going to be a minus x squared. I can do that numerator. This one is going to be, we're going to multiply, 2 times 2x, which is going to be 4x. And then root 5 minus x times root 5 minus x is going to be this thing squared. So it's going to cancel that radical. So this will just be a 5 minus x. And simplifying, I can distribute that 4x through. 4x minus 4x squared minus another x. Sorry, that should be 4 times 5. That should be 20x. 4x times that is minus 4x squared minus another x squared. All of that 2 times the square root of 5 minus x. So this is going to be 20, and those x squareds will combine to minus 5x squared. So we have to figure out, where this thing is equal to 0, and technically also where it's undefined. So we didn't bring out where it's undefined before because we were working with polynomials. We'll do a rational in a second here and talk about undefined too. But remember, undefined can, functions that are undefined can be at sharp points. You won't find a derivative equal to 0 here, but that definitely is a maximum. So things like that can show up, and also asymptotes can show up as well, because we have to be careful. Sometimes a function might increase before the asymptote and decrease after. So, this is a spot where functions can change from increasing to decreasing. So, if this had a local something here, you might not, you might miss this because you're like, well, it's increasing before and increasing after. So you have to make sure to take into account those asymptotes. And it's also possible it could look like a radical and it could stop at that particular spot where it's, where it's equal to 0. So it's just kind of what's going to happen. So first, when this is equal to 0 or undefined, so the simplest thing equal to 0 or undefined. A fraction's equal to 0 when the numerator is 0. So this would be when 20x minus 5x squared is equal to 0. And this is a polynomial, so we can just count factors. So let's factor out a 5x. And this would be 4 minus x is equal to 0. So, I got two factors, 5x equal to 0 because x is equal to 0. And for this one, x is equal to 4. Now, where it's undefined is going to happen. Is going to happen when the denominator is equal. So this is 2, 5 minus x is 0. Divide by 2, so 5 minus x is 0. Squaring both sides, and then adding x. So x is so we get those. So those are critical points. So if you look at like the axis, you're going to see, I'm going to have 0, I'm going to have 4, and I'm also going to have 5. So we're going to have to check, these intervals. So our intervals would be minus infinity to 0. This is going to be 0 to 4. We're going to have 4 to 5. And then we'll also have 5 to infinity. One of these will break, and I'll explain why. Okay. So I have to pick x values. And then we'll have to type those x values into f prime of x to figure out if it's increasing or decreasing. So, an x value in here, I'll pick that 1. It's a nice number. X value here, 1, that's a nice number. And I'll pick 4.5. It's good that I get. And over here, let's pick x 6. So remember, we're typing this thing, we're plugging these things into the derivative, which is right here. That's our f prime of x, right? And we'll see what happens. If you have this messy thing in the derivative, don't forget, if you're going to plug it into a calculator, like in the y equals, don't forget to put the numerator in parentheses. And also, since the denominator is a product of two things, don't forget to put that in parentheses as well. Here we have 20x minus 5x squared divided by 2 second square root of 5 minus x. And then we'll figure out what their values are. So negative 1, 1, 4.5, and 6. So negative 1, I get at negative 5.103. I don't. But all I know is it's negative, therefore it's decreasing. 1, I get 3.75, but it's a positive number, so that means it's increasing. 4.5, I get negative 7.955. It's a negative number, it's decreasing. And 6, I get an error. So the question is, why do we get an error there? Well, if we go back to the original function, we know that radicals have domain restrictions. So if I looked at something like y is equal to the square root of x, we know that that function looks like this, that the domain would be 0 to infinity. So this has to have something similar to that. So let's look at its domain and see what that's all about. Well, its domain is going to happen when, all you do is look at the radicand. All I know is what's underneath this radical. What's underneath this radical has to be greater or equal to 0. So you ignore the radical. You just have to say what's under the radical, the radicand, has to be greater or equal to 0. So 5 minus x has to be greater or equal to 0. So minus x has to be greater than or equal to negative 5. When you divide by a negative, it flips that sign, so less than or equal to 5. So this less than or equal to 5 means that technically this is an endpoint. Because remember, radicals have endpoints. This just goes the other way. So it's going to have some endpoint, maybe like this, or maybe uphill to that, but it's going to have an endpoint. So really, this is closed at 5. And this is not even in the domain. That's why we added third. So that means 5 is an endpoint because the closed part of a radical. So 5 is something that we have to take account. So we have to look at 0, 4, and also this 5. So all I know is that here, decreasing before 0, increasing after 0, that means that's a local min. So we should say x equals 0 is a local min. Here it increases before 4, and then it decreases after 4. So x equals 4 is going to be a local max. And remember, 5 is an endpoint. This thing is going to decrease to 5. It's going to decrease to 5. Since it decreases to 5, that means x equals 5 is a local min. careful on radicals. You know, I'll throw it on a test. So, you know, what's that? That's number 4.3. That's number 22. So maybe look at 21 as well. So know how to do 21 and 22. That's just your so 4.3. I think that's the numbers. So I have an older version of the book, so I'm not sure if it's the same one, but look at the one that's right next to this one as well. I said I was going to do a rational. Let's do one rational because it's quick and talk about its local extreme. Actually, we have to graph. I forgot about that. We have to do a lot more than that. This is just local extreme. We got to graph and make fun things. We might be here a while. Forgot about that. So let's do a polynomial, and then I'll do a rational, and that should be it for that stuff. So, all right, that's good enough. It's just simple. To make sure that it has inflection points. Yeah, so x cubed minus x plus 3. Let's go graph. F of x is equal to x cubed minus 3x plus 3. So when I ask you to graph these, we have the steps that ask you to go through, and I actually label the steps here on the test, like, you know, identify the domain, then I ask you to find the derivatives. So I'm just going to kind of go through all this. So I'll have to eventually. So one, you know, what's the domain? Well, since this is a polynomial, you know, the domain is going to be minus infinity. There's no division, there's no radicals, so the domain is all numbers. Two would ask you to find, you know, y prime and y double prime. Well, the derivative is going to be 3x squared minus 3, and the second derivative is going to be the derivative of this is going to be 6x. Number 3, it asks us to find the critical points. This is identify the behavior at each one of those. I'm kind of ignoring it because we're going to find increasing and decreasing. So that question's answered in the next one. So let's find the critical points. Well, we know the critical points happen when f prime of x is equal to 0. So setting 3x squared minus 3 is equal to 0. Factor out of 3, I get x squared minus 1. That's a difference of squares. So x plus 1 times x minus 1 is equal to 0. So I get x is equal to negative 1. I get x is equal to positive 1. So those are critical points. Number 4 asks us to figure out the intervals for which this thing is increasing and also decreasing. So really, except for the exclusion of y double prime, most of this is just the first derivative test, what we did in the previous two problems. So increasing and decreasing, then we can figure out local extrema. So I know that the intervals are going to be, you know, if this is cut at -1 and +1, we have, you know, minus infinity to -1. We're going to have -1 to 1, and we're also going to have 1 to infinity. So then we choose an x value in here. So -2, x value here maybe 0, x value here 2. And then we'll plug it into the first derivative. This is what tells us if it's going up or down, right? Increasing and decreasing. So clear, we have, remember we're to figure out increasing and decreasing, we're doing the derivative. So 3x squared minus 3. And then we can plug in these values. So negative 2, 0, 2. So I get 9 for this, but positive 9, therefore this is going to be increasing. 0, I get a negative 3. So since it's a negative number, it's decreasing. And 2 gives us 9, so this is a positive 9. Does it ask us to tell us local extrema now? Well, it doesn't, but I'm gonna say it anyway. So if it's increasing to decreasing, if it's increasing before -1 and decreasing after -1, x equals -1 is a local max. And if here it's going to be decreasing before 1, and then it's going to be increasing after 1. So that means, x is equal to 1 is a local min. So really most of the work that we've done here is just like the previous two problems. 5 is going to ask us to find any points of inflection. Well, your points of inflection, sorry, I forgot to say, this is when the derivative is equal to 0 or undefined, but polynomials don't have this undefined problem. Your undefined parts will happen if it's going to be rational or radical and stuff like that, so they have to be special functions. So that's why I'm ignoring the undefined here. And the next problem, undefined will be important, but polynomials are very easy to have. So inflection points. This happens when, the second derivative is equal to 0 or undefined, but, the second derivative being also a polynomial, it's not going to be undefined anywhere. So this is when x is equal to 0. So when it wants the behavior at these intervals, your inflection points tell us the difference between stuff being, concave up or concave down. Something that might be concave up, that's increasing concave up, that's increasing concave down. Concave up means that the U shape is going up, right? Concave down means the U shape is pointing down. So these are two types of graphs. So it's nice when we're graphing, we need to know their shape if they're increasing or decreasing. So the same thing when it comes to decreasing, we need to know their concavity as well. So I know that just like increasing and decreasing, it's only going to change where that first derivative is equal to 0. So concavity is only going to change where that second derivative is equal to 0. So it's only cut at 0. So our intervals here are going to be minus infinity to 0 and 0 to infinity. The first derivative, which we call the first derivative test, will tell us increasing and decreasing. The second derivative test will tell us concavity. So we're going to plug these things into the second derivative, and we're going to figure out if it's going to be concave up or concave down. Positive being concave up, negative value meaning concave down, negative output, after the prime. So picking a number in here, -1. Picking a number in here, we'll pick 1. And remember that we're plugging them into the derivative, into the second derivative. So we're plugging them into this thing, into this one now. So 6 times -1 is going to be -6. So that means this is going to be concave down. Plugging 1 into 6x is going to be +6. Positive means concave down. 6 says identify any asymptotes. I'll write it over here. 6. Any asymptotes? Well, asymptotes happen really with with certain functions, and polynomials don't have asymptotes. So when we get to a rational function in a second here, it will have asymptotes. So that's why I write 9 here. But number 7 is going to finally ask us to graph. So graph, what I want to do is I want to graph all these special points that we found. So I need to graph this x equals -1, this x equals +1, and also this this x is equal to 0. So I'm also going to need to know these as well. I know the book asks you to find all x-intercepts and so on, but really just find the points that came from calculus, like your local extrema and then your inflection points, and you'll get yourself a nice enough graph that's acceptable. So I'm going to plug these things into the original function so I can figure out their y value because I'm going to graph them. So I need to know what is f of -1, what is f of 0, and what is f of +1. So remember this one now. So x cubed minus 3x plus 3. And our table, we got -1, 0, and 1. So I get 5, 3, and 1. So when I graph this, -1, 0, and +1. At -1, I get 5. At 0, I get 3, and at 1, I get 1. Now, remember, it's not just some straight line that runs through those numbers. These things have increasing and decreasing and concavity and so on. So what I know is, like, before here, say x equals -1. So from -infinity to -1, -infinity to -1, this thing is increasing. So it means it's going uphill. Also from zero, from -infinity to 0, so actually from all the way to here, let me cut this here, look at it this way. To the left of this dotted line, this is going to be concave down. Hopefully you can see this in the graph. But over here, I doubt you can. I can see it. So this is going to be concave down. So increasing concave down means it's going to look like this. Increasing concave down. Again, to the right of this is going to be concave up. So over here is going to be concave down as well. But from -1 to 1, it's going to be decreasing from here to here. But here it's going to be decreasing. It's going to be decreasing from this interval. But here it's going to be decreasing in concave down. Decreasing concave down. But over here, in this interval, it's going to be decreasing but concave up. So decreasing concave up. And then last, we have from 1 to infinity, this is going to be increasing. It's going to be concave up over here. So it's going to look like that. Okay. One more of these and we'll get to optimization. That'll be our last problem. So we got about another maybe 10 minutes. So the next one I want to do is something like still graph f of x is equal to let's go like x minus 1 all over x. Let's say x plus 1 all over x minus 4. Something like that. That's good. Oh, do I have a better one? Let's see if we can see. That's a good one. You know what? What the heck? A little mess here, but it's fine. Let's do this. Let's do x squared minus 3 all over, let's say x minus 2. So the first thing they ask us is they want to know the domain. So that's the very first one. Well, since this is rational, I can't divide by 0. So this is going to be every number except what makes the denominator 0. So the thing that makes the denominator is equal to 2. So I have to just exclude 2. So minus infinity to 2 and then 2 to infinity. 2, they're going to ask for the derivatives and the second derivative. So y prime. Y prime is going to be, well, this is a quotient. So derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Since it picks up something messy. I don't care. So when we're done here, this is going to be 2x squared minus 4x minus x squared plus 3 minus x squared plus 3 all over x minus 2 squared. So we're going to get, you know what? This is so messy. I wouldn't put this. We'll finish. Fine. we'll finish it. Doesn't matter. Okay, so 2x squared minus x squared is going to be x squared. This will be minus 4x minus 3 all over x minus 2 squared. So that's actually that factors. That's kind of nice. So this is going to be x minus 3, x minus plus 3, x minus 1 all over x minus 2 squared. Unfortunately, nothing cancels, but when you have something in that form, because remember, if I want to find critical points, it's when the top is 0 and also when the bottom is 0, because it'd be undefined now. So second derivative. So easier. Oh well. Second derivative. Y double prime. Derivative of the top times bottom minus the top. Derivative of the bottom. 2 times x minus 2 to the first power times the derivative of the side would be 1. All over the bottom squared. X minus 2 squared, which would be x to the fourth. Ugh, gross. Well, here's something that's kind of nice. I see an x minus 2 in all these spots. You know, this is all multiplication. This is all multiplication. So if I cancel an x minus 2 from 1, I can do it. As long as I do it from all three spots, I'm good to go. So this is going to be, I can only cancel, since this only has one of them, I can only take one for every spot. So this will be 2x minus 4 times x minus 2. Minus 2 times this. Well, that gets to go away. I'm just going to distribute 2 times x squared minus 4x plus 3. This is a brutal mess. I might eventually abandon this. I would never ask this on a test. Not to find first and second. You know, this would be a good problem for. This would be. Let's talk about this. Let me use this. This would be a really nice problem if I was only going to ask you for local maxes and local mins. I would ask this on a test because it'll take you like a half an hour to do this problem. But that'd be a pretty good problem to find local maxes and local mins because this thing factors so nicely. So if you want to find, you know, our intervals, we can see that, you know, when this thing is equal to 0, you're going to get x is equal to 3 and x is equal to 1. Or if this thing is undefined, you're going to get x is equal to 2. So we have to be careful with your undefined. So if you're looking at the intervals, I am going to cut at 1, 2, and 3. 1, 2, and 3. So you'd have minus infinity to 1. You'd have 1 to 2. You'd have 2 to 3. And then you'd have 3 to infinity. And then you'd have to pick an x value at f prime of x. The reason why I bring this up is because remember, since this is a rational expression, you know, you're going to have spots to where the derivative will be undefined. So don't forget about the undefined part. So, you know, pick x's in here and you can do increasing and decreasing. This would be a good problem for that. I'm gonna make this a little easier so I have to be here for half an hour. Let me do a rational that was like the first one. Let me get messy, but we're both running out of steam here. At least I am. So let me just do a different beat. Let's do the one I was going to ask before. So x plus 1 all over x minus 4. Well, number one, I have to look at the domain. The domain is going to be, well, when the bottom is equal to 0, I have to exclude that number. So it'll be, you know, I have to get rid of 4 because I don't like the denominator 0. To the derivative. Well, derivative of the top, y prime. Derivative of the top will be 1 times the bottom minus the top times the derivative of the bottom all over the bottom squared. So this will be x minus 4 minus x minus 1. Don't forget to distribute that negative to both of those. All over x minus 4 squared. So this is going to be minus 5 all over x minus 4 squared. For the second derivative, I would rewrite this like that, because the second derivative would be much quicker if you did it this way. Though the quotient would be fine because the derivative of the top would be equal to 0. So if you did it this way or if you did it this way, quotient will derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Squared is going to be fourth. You can see that this goes away. So what I'm going to get here is a negative, which is a positive. So this is going to be 10 times x minus 4 all over x minus 4 to the fourth. So one of those x minus 4s will cancel. So this will be 10 all over x minus 4 cubed. And you can see if I did the derivative here, this times this is 10, x minus 4 to the negative 3, which is what you do right there. He's going to ask for intervals. Well, when you're looking at a function, if you want to know intervals and increasing and decreasing, we have to look at the derivatives. And when you need to know when this is equal to 0 or when this is undefined. The problem is the only way for a fraction to equal to 0 is if the numerator is 0. And since the numerator is a constant, that'll never happen. So, when is f prime of x equal to 0? Well, this would be when minus 5 is equal to 0, which can't happen. Or it's going to be when it's undefined. So it's undefined when the denominator is equal to 0. So that would be when x is equal to 4. So our intervals are going to be minus infinity to 4 and 4 to infinity. So then we'll pick an x value and plug it into the derivative. So I don't know, let's pick 0 and pick 5. Any number inside this interval works. If you wanted 3 instead, sometimes you used to do these things by hand. It'd be easier to plug in 0, right? So negative 5 over negative 4 quantity squared. So negative 5 over 16 would be a negative over a positive, which would be a negative number. So I know this is going to be a negative number. But we can also just type that into our calculator. Minus 5 divided by x minus 4 quantity squared. And we can do 0 and 5. So I get negative 0.313. And here I get a negative 5, which is interesting because notice how they're both negative. It means this thing is decreasing before, and it's also decreasing. So when we do number 5, which is going to be the inflection points, and then also we'll have to cut the intervals bigger concavity as well. So inflection points / concavity. The inflection points happen when the second derivative is equal to 0 or undefined. So we'd be looking at the second derivative, which is going to be this one. So 10 all over x minus 4 squared equal to 0. This is when 10 is equal to 0, which means no solution. But undefined is when the bottom would be equal to 0. So this is when x minus 4 cubed is equal to 0. Cube rooted x minus 4 is equal to 0. So x is equal to 4. So it does have an interval that we have to cut. So our intervals for our inflections are going to be minus infinity to 4 and also 4 to infinity. It just happens to be the same, the same cuts that we made last time. But it's not always, right? In the previous example, they were different. So we're going to pick an x value, and if I want to determine concavity, I have to plug them into the second derivative. So I'll plug a 0 and 5 in. Why not? Remember that we're doing the second derivative, so I have to use this function. So clear 10 divided by x minus 4 cubed. Plug in those numbers, so I get this one gives me negative 0.156, and this one gives me 10. But a negative for the second derivative means this is concave down. Positive means this is concave up. Now, asymptotes. The reason why you have to exclude that x equals 4 is from your algebra class. Remember that when the denominator is equal to 0 of a simplified rational expression, that means that x equals 4 is a vertical asymptote. Now, in the very first section, we could take the limit as x goes to infinity of this thing. And what you'll notice is it'll shoot to a negative infinity from the left, and it'll shoot to negative infinity from the right. The reason why I know that is those decreasing. Actually, it'll shoot to negative infinity from the left and positive infinity from the right, which will prove that's an asymptote. But it's good enough to say that we have a vertical asymptote. X equals 4. Also, from the very first exam, this thing has a horizontal asymptote. What you do is you take the limit as x goes to infinity of this thing. So you multiply top and bottom by 1 over x. But what you're going to get is you get those leading coefficients, which will be 1 over 1. So if you take the limit as x goes to infinity, you'll see that that this is going to have a horizontal asymptote. Y equals 1. So again, the way you find this vertical asymptote, if you wish to prove it, you could take the limit as x goes to 4 from the negative side of x plus 1 over x minus 4. So you'll see that you'll get this will be a positive. This is below 4 over negative. So this will be negative infinity. And if you did it from the positive side, you'll see that this will be positive infinity. So that's why you know that it's going to do something like this with an asymptote. You want to prove that this is a horizontal asymptote. Take the limit as x goes to infinity of x plus 1 all over x minus 4. And you multiply top and bottom by 1 over x. So you're going to get 1 plus 1 over x, 1 minus 4 over x. But we're taking the limit as x goes to infinity. So this is going to be 1 plus 0 over 1 minus 0. So you get 1. I don't, at this late stage in the game, I'm really okay with you guys just using the techniques of algebra to verify that these things are asymptotes. I'm not asking you to prove it with limits, but to throw back to what you guys did in the very first chapter is nice to see again. But again, this is enough. You don't have to show that at this test. So when we have to graph this for number 7, notice there were no critical points. The only spot that we split this was at an asymptote. So I'm not going to graph any critical points. So all I'm going to be able to do is graph asymptotes and then talk about increasing and decreasing in concavity. So what I know is I know that this function has a vertical asymptote. This thing has a vertical asymptote at 4, 1, 2, 3, 4. A vertical asymptote at x equals 4. It's got a horizontal asymptote at y equals 1. Now, I know over here, from minus infinity to 4, over here, this is going to be decreasing. And also from minus infinity to 4, this is concave up. So for this thing to be decreasing and concave up, well, the only way for, concave down. The only way for this to be decreasing concave down, which means it'd have to live in this section, it'd have to look like this. It'd be asymptotic here and shoot off to negative infinity here. So that's the way it would work. Decreasing concave down. I know over here we are decreasing, we are concave up. So to be decreasing concave up, you get this. So that's what the graph looks like. What's interesting about this rational one is there were no critical points. There are just asymptotes. Same thing here. No inflection points, just asymptotes. This doesn't have an inflection point, but the asymptote was the spot where it changed its concavity. Now the last one, let's do let's do one optimization problem and then call it a day. I don't even want to know what time it is. Best fencing plan. I love it. Okay, so a rectangular plot of farmland would be bounded on one side by a river and the other three sides. Sure, let's do that. So, what these optimization problems do is it's really like a system of two equations, and then you have to take the derivative of one of them, but you have to solve the system kind of first. When we take derivatives, we're only really allowed in this particular section like one dependent variable. We don't want to have a whole bunch of independent variables because I don't have enough information. But I do know that one variable is related to the other. That's what I mean by a system. Is that one equation relates the variables, and the other equation we're going to have to optimize. And optimize really means find the max or min. So which means take its derivative and set it equal to. I don't know, maybe do two. So expect this to take this long. Okay, so this is a rectangular farmland is going to be bounded on one side by a river. So optimization. So example, rectangular farmland bounded on one side by a river. So, and the other three sides by a single strand of electrical fence. And other three sides by a strand of electrical fence. With 800 meters of wire, what is the largest area you can enclose? 800 meters of wire. What is the largest area we can close? And then what the heck? What are the dimensions? What are the dimensions of the rectangle? So what's really cool here is when you look at like here, I got a wine glass here, but like if you look at like soda cans, for instance, I know this is three-dimensional as opposed to two-dimensional areas, but if you look at soda cans, you notice that they all have the same shape. And they're kind of the big reason by that, besides just storing. There's other variables included as well. But one major reason is we're trying to hold 12 ounces of liquid in the smallest amount of aluminum that we can use. So we are restricted by a bound, and we're trying to minimize that. So it's cool that cans can be super tall or super fat, right? But if you change their shape, you're going to change how much aluminum that you use, and that's expensive. So it's kind of cool that with 800 meters of wire at my disposal, I can actually make a farmland that'll give us the most area possible. Especially if you're trying to feed cattle, you want to have as much grass as possible. So do you make it really long and skinny? Or is it going to be somewhere kind of in the middle? Is it going to be a perfect square? Is it going to be a perfect rectangle? Well, it kind of depends. What's interesting is if it was just four sides that wasn't a river, it'll actually just be a square. It's kind of cool. But since we're bounded by a river, I don't actually have to strand the river side. So what I have is I have a rectangular fence here, but over here I have a river. So I'm not going to put electrical fence on that river, which means it's going to change the shape of this thing. It won't be a square anymore. So what I'm going to do is I'm going to label this. I call it this. Let's call these the length and this the width. So what's cool here is we're going to have two different equations. One represents how much string I use or how much electrical fence I use, and the other one has to do with the area. So we have two different equations. I have the fence equation, and I have the area equation. Now, one of these equations, I'm going to take the derivative of it. It depends on what I'm trying to maximize. So the fence, all I know is that I have 800 meters of fence. So I have so let's just call it half. Fence is going to equal. Well, this is my fence. I have to fence these spots here. So the fence is going to be, L plus W plus L. You don't have to fence that area. Now, what I do know is that the fence is 800 meters. So it's a fence with 800 meters. So 800 is going to be equal to, 2L plus W. Now, the next it says that I want the largest area. Well, the area that I enclose is going to be this. This is going to be my area. And the way to find an area this is a rectangle. The way you find the area of a rectangle is going to be the multiplication of its two sides. So area is equal to length times width. So there's your two equations. One of these I'm going to take the derivative of. The other one I'm going to use to simplify or reduce the variables here. So when it asks us for the largest area, I need to optimize this one, which means I'm going to take its derivative. But I don't want to take the derivative of this. I don't want to have multiple independent variables. I just want this to be one dependent, one independent. So what this equation allows us to do is it allows us to rewrite this side of the equation as just either W's or L's, and it's kind of your choice what you want to use. So what I'm going to do is I'm going to look at this equation. I'm going to say, well, what's the easiest letter to solve for? Well, W here. So I can say 800 minus 2L is going to be equal to W. And now I can plug that into the W. So the area is going to be equal to L multiplied by 800 minus 2L. And I don't want to take the derivative that way. It's easier without parentheses. So 800L minus 2L squared. Now, instead of this thing having two independent variables, it just has one. This equation this is that system of equations kind of thing I'm talking about, that you use this to reduce the variables. Now I'm going to optimize, so that means I'm going to take the derivative of this. So A prime is going to be equal to, the derivative of this is going to be 800, and this is going to be 4L. And the way you optimize, the way you find your maxes or mins, is you take this derivative and then you set it equal to 0. So just setting this equal to 0, let A prime equal to 0. So 0 is equal to 800 minus 4L. So 4L is equal to 800. So L is equal to 200. And once you know L, you can plug it back into here, and you also know W. So 800 minus 2 times L, which is 200, is equal to W. So 800 minus 400, 400 is equal to W. So they ask, what's the largest area? The largest area is going to be area's length times width. So it's going to be the multiplication of these things. So it's going to be, L times W. So 200 times 400 is going to be 8 with 4 zeros. So 80,000. And the dimensions are, the dimensions are, 400 by 200 or 200 by 400. I don't care what order. I think that's really the gist of these optimization problems. Is they ask you to optimize an equation, and they usually give you another one to reduce the variables, and it's kind of the same thing over and over and over again. Though they get more and more complicated as you go on, but I guess pretty middle of the road problems when it comes to a test. And that's it. So I didn't ask you for many questions because we're trying to get stuff going here, but I hope that helped, Noel. You got any questions for me before I sign off?
No, thank you.
You're welcome. Sticking around. That was a long time.
It's okay.
Have a good one.